Hello, my name is Michael Janke, and today I'll be discussing motorcycle accidents and injury severity in France in order to understand the factors that influence injury. I also have a personal interest in that I am a motorcycle rider myself, and I have an interest in staying alive. So some statistics about motorcycle riders. They have a 28 times greater risk of fatal crash than car drivers do. 78.3% of motorcycle accidents result in injury, and just over 4% of those are fatal. You compare that to cars, where 31% result in injury and only 0.29% of them are fatal. So the goal of this research is to understand what factors have the most influence on accident severity, either fatality or severe injury. Also to evaluate several machine learning methods and their performance in trying to achieve this goal. I'm not trying to do anything with accident prevention because there's no source data for that. We don't know what factors were involved in accidents that didn't actually happen. So the data source comes from the French government, the French Ministry of Interior. It's accident survey data collected in mainland France and some of its island territories between the years of 2005 and 2017. The data is also in French, so I had to translate that. 839,985 accidents were recorded, including places, vehicles, and users. So I did some processing up front to join those four tables together. I restricted the observations to motorcycles owned. I did not include mopeds or scooters because they're a bit different, and also restricted to mainland France so that we could avoid unknown cultural and traffic law influences. So in the end, just over 58,000 accidents were recorded in this data set. So after that, I did some distribution evaluation to determine which features to keep and which to get rid of. I also removed some observations where there were missing values with things like age and location. Nearly all the features were categorical, so I encoded those into dummy variables, but engineered a couple of features for age range and time of day. So the result was just over 51,000 accidents left to work with. So looking at the distributions, about 37% were severe, about 3.5% were fatal, male versus female. So 92% are male riders, 8% are female, but looking at fatalities, 96% of males were fatal compared to 4% of females, so a little bit higher for males. Age range, the highest occurrence rate was with 20 to 29 years old and steadily decreasing until they got into their later years. But for under 20 and those over 60, that's more likely due to the fact that they've not a lot of riders. 89% of French riders in this data set wear a helmet compared to 11% that do not. So I created two class variables, one for fatal versus not fatal, a little imbalanced with only 3.5% in the fatal group, and then severe versus not severe, which included fatal and severe injury, which is a little more balanced with 60% versus 40%. So looking at some of the different machine learning methods for the fatal class decision trees first. So not very good performance here for either the training test or cross-validation. We got a F1 score of 15 versus 9 for cross-validation, but we did get an 85 F1 score when we balanced the data, but I'm not very trusting of that, which you'll see why in a second. So looking at random forest then, even lower scores here. F1 with 0.05 for train test and 0.06 for cross-validation, just a little bit better this time. But then we get 0.96 for balancing with a 1 for AUC. I don't believe in the predictive power of this, so I think something's going on there with the balancing method and possibly some overfitting going on. So for fun, I also included logistic regression just to compare those. The score here for a train test was actually better than random forest with a 0.09, but then again, consistent with 0.5 for cross-validation but higher for balancing. These are still terrible scores, so I wouldn't hold much to this, but it was just interesting that logistic regression did a little bit better. Looking at the severe class, more balanced, so I'm expecting better results here. So looking at train test split, we get a 0.53 for F1, which outperformed cross-validation at 0.49. I didn't do any balancing with this data set, so there's nothing to show in that column. Accuracies are lower than but AUC and accuracy here are closer together and indicating balance. Random forest, F1 of 0.56 compared to 0.50 for cross-validation. And then for interest, I included feature selection here of 0.48, so it was less. I did do feature selection on a lot of the other ones, but I just included it here just to show that it was done. But it didn't perform very well compared to the other things, so I didn't include it. Lastly, logistic regression for the severe class and train test. 0.58, which was the best F1 score out of all of them for severe, compared to 0.49 across validation here. I did not perform feature selection here for logistic regression. So I think logistic regression is the winner here, actually. So some discussions of the results. So in the fatal class, the best performance was the random forest with balance, but again, I'm suspicious of that. So I'm going to ignore that and call the best performance a 0.15 for decision tree. But because it was imbalanced, these feature importances are probably not all that relevant, but I put them there just for interest. Better yet, with the discussion of the severe class here, we had the best performance for logistic regression of 0.58. So the feature importance was a bit hard to interpret with the coefficients. So I actually looked at random forest to look at these features. And on the top were department road, without changing direction. They struck a pedestrian. The trip was for leisure, and they were in the city. So some issues here. The imbalance of the fatal class was troublesome, and the SMOTE method of balancing it needs to be reviewed and validate the result. I could have introduced some subtle bias by arbitrarily choosing some buckets for age and time and using my gut to remove features. I tried SVM, but I had to get up. It ran for over an hour without completing, so I just did not continue with it. There were some additional issues that, in my opinion, with the data itself, there were some missing features that I think obviously should have been collected at the accident, such as alcohol level, speed, did they have a valid motorcycle license at the time, and how long had the rider been licensed at the time of the accident. So some future work. I used my trial and error for finding optimal parameters. I could use grid search. I could try some additional machine learning methods such as boosting and neural networks. I could address the class imbalance issue to try and do something with the fatal class, and also look for some other data sets that have relevant features. Thank you.